All right, so this is trying to finish up some of the questions that I did not get to in the review. So this is my list of questions, but first, the one I was asked at the very, very end that I gave a verbal answer to that was not great, which was essentially, when do we need Avogadros number? Avogadros number. I am so sorry, my spelling keeps getting worse. So the whole idea of Avogadros number is it is, in fact, just a number. So when we talk about things like a dozen is equal to 12, Avogadros number is equal to 1 mole. Now, Avogadros number is a big number. It's 6.022 times 10 to the 23rd, but it is just a number. It's much more difficult to wrap our brains around because 12 is, well, 12, whereas this one's got lots more digits, but the idea is the same. So when we are doing any particular calculation, like for example, let's say that I had 186.21 grams of rhenium, and I wanted to know how many atoms I have. What I would do is, since this is in grams, I can use a periodic table to go from grams to moles. And then whenever I want atoms, this is going to be when I actually use Avogadros number, because that's how I'm going to get to atoms. So there are 6.022 times 10 to the 23rd atoms in 1 mole. And this is what relates us back to the mole, well, it relates us back to the periodic table. So the whole point of using this number is it allows us to use all of the different values in the periodic table as grams instead of just as atomic mass units. So I can go to the periodic table, and I know I scribbled on this a lot, but there's rhenium. So I'm going to use the average atomic mass that's hiding way down there in this problem. And so I can go ahead and take my 186.21 grams. Oh, sorry, that's not what I wanted to do. That's my number of grams per mole. I guess we're just going to go ahead and say that that's how many I have. Cheating, that means I have 1 mole, but we'll go ahead and still do this. So that's how many grams I have, because that's what the problem told me I have. And then from the periodic table, I have 186.21 grams in 1 mole. And then what I'm going to do next is say that in 1 mole, I have 6.022 times 10 to the 23rd atoms. And granted, since this number and this number are the same, I have 1 mole, and that means I just have that many atoms. I will go ahead and do one more example so that we can go backwards. But essentially, when we use atoms, that's also, whenever we have atoms, that's when we're going to want to use that big number. Because otherwise, moles are usually smaller than that. So I could also say, well, what if I had something like 4.23 times 10 to the 25th atoms? We'll go ahead and do of golds, and we'll say, what is the mass in grams? So again, I have the word atoms, and that really is going to be one of my keys. Also the fact that I'm going to grams, because this essentially, if I'm going to go to grams, I need the periodic table. And so that's how I'm going to get there. So I'm going to go from atoms to moles. And then in 1 mole, I'm going to look on the periodic table and find golds, just down here, 197.0. So now I can go ahead and multiply by everything across the top, divide by everything that's on the bottom. Because one of the other things you should note is, if you ever are starting in atoms, everything should get a lot smaller. atoms themselves are very small things, which means we tend to have a lot of them in any particular set. So starting off with a whole bunch of atoms makes a lot of sense. Our grams, therefore, should not have times 10 to the 25th or times 10 to the 24th. This should get smaller overall, but granted, it's not super hard to do, but it should get smaller number. Should not have times 10 to the 40th grams, because that's a lot. 7.8 grams. So atoms are tiny, tiny little things. So there should be a lot of atoms in anything. Grams should be a smaller number than the atoms, and they are. So hopefully that helps with when to use Avogadros number. So next up, this is a clarification on one of the other problems that I did. So I'm going to scroll back up. So this is a follow-up. So what you're watching right now is a follow-up video to the exam review. So for the frequency question, whoopsies, this was really helpful if I make this smaller. Where's my frequency? There's my frequency question. So for the frequency question, what I did is I started off here on the left, and I said I had a wavelength of 12 millimeters. I took the 12 millimeters and I converted that. So my actual conversion factor, or pardon me, my constant, the speed of light, I left alone. So I left the speed of light in meters per second. So 2.998 times 10 to the 8th is meters per second. I left that number alone. I changed the wavelength to be meters. So what you should notice then is in the math itself, when I start to actually put things into the equation, I have meters on both sides. So this was the point I was trying to make before, is that my whatever length units I have need to be identical. So if you wanted to, you could change the constant. I don't. I change whatever the given information is, and I don't change the constant. But the point is that they need to be the same, whatever they are. So I changed the wavelength here. So originally this was 12 millimeters. I went ahead and said that for 12 millimeters, for every 1 meter, I should have 1 times 10 to the negative 3 meters, which gives me my new value in meters. So I changed the wavelength number, and that's what I changed. So I changed the wavelength number before I put it into the equation, but I left the speed of light alone. So that's what I did over there. Scrolling back. How similar will the multiple choice answers be to each other? So this, it depends on the question. I know that doesn't help you a lot. So honestly, I'm just going to tell you to see the 2019 exams. Because I can give you a whole bunch of different ideas and you will still want more. So I'm just going to go ahead and tell you to see the 2019 exam, because that way you can look at multiple different options. Do we know the electrostatic equation or the kinetic energy equation from chapter 3? No. You should be comfortable with the word electrostatic. So if the term electrostatic bothers you, this is really just referring to positive charges interacting with negative charges. So whenever we say electrostatic interactions, we're talking about positives and negatives, or positives and positives, or negatives and negatives. So when we talk about electrostatic interactions, we're talking about charge interactions. So no on the equations, but yes on terms. So you should be okay with the word electrostatic and electrostatic interactions, because when we're going to talk about things like electrons being repelled by each other, protons being repelled by each other, protons and electrons being attracted to each other, all of those are examples of electrostatic interactions. It's the broad term. So that you should be okay with, but equations, no. We're not going to use those. I like to show those off just because there are folks who are familiar with those equations already, and I like to show them connections because a lot of times they're just like, chemistry doesn't relate to anything. And it's like, oh, yes, it does. Relates to lots of stuff. Are there any other calculations we should be comfortable with other than the ones you already talked about? So this is always a valid question. I always appreciate it when people are asking, like, is there anything else that you missed? So this is the part where I do some preparation, but I don't do a complete preparation. So I'm trying to think if there are other things that are legitimate calculations. So there are some oddball ones that I personally never think of as being calculations. But some people do. So I'll give you an example. In quantum numbers. So the bottom line is going to be yes. There are always calculations that exist that you are responsible for that I don't remember. There's always something. So for example, in quantum numbers, if we ask something like how many orbitals are available in the D subshell. When I think about this question, I personally answer it like this. The D subshell, that is L equals 2. When L equals 2, my options for M sub L start at negative L, which is negative 2. They go to 0, and then they go to positive L. So those are my options for M sub L, and that's 1, 2, 3, 4, 5 options. So then I would just count them, and I would tell you that for every value of M sub L, that's 1 orbital. There are 5 values for M sub L, that's 5 orbitals, and I'm done. So that's how I actually do that. So for me, that's not a calculation because that's using the rules of quantum numbers to figure out how many values there are and then counting them. So for me, it's not a calculation, but Alex and other things will be like, oh, how many orbitals are in the D subshell? I'm going to take this L equals 2, still valid, and then what I'm going to do is I'm going to plug this into a formula that Alex gave, which is 2L plus 1. And that is therefore 2 times 2 plus 1, which is equal to 5. And that's the answer. I have no idea which way you prefer. So this is another one of those times, because the hard thing is there's more than one of these quantum number formulas, and I don't ever use them. So there are times when they are valid and people find them useful, but I personally am more visual when it comes to quantum numbers, and I often link quantum numbers to orbital notation, so I never remember the other equations that you can do. So some of y'all may be more familiar with that, and if you are, more power to you. That certainly works, but I don't usually do that. So that's where I land on that one. As far as other calculations, one of the tricks I always struggle with is that there is just some amount of like basic mathematics or reading questions correctly that we expect y'all to be able to do. So there's not any particular other ones related to chemistry that I can think of at the moment. If I do, I will let you know, but otherwise I'm going to move on from that. And I'm just going to also recommend you ask everybody. So when you're trying to figure out what other calculations there could be, just ask everybody. See what they come up with. Do we need to know how to find the velocity from a de Broglie wavelength? It was a question on the 2019 exam. Nope. You should know on this equation. As far as de Broglie wavelength, the concept you need the idea that as wavelength, oh, wrong way. This doesn't make as much sense when you do it that way. You do need the idea that as your mass increases, the wavelength decreases. This is the main reason why we care about wavelength for electrons. Their mass is teeny, teeny, tiny. and why we do not care about wavelength for protons, and we do not care about wavelength for atoms, and we don't care about wavelength for a car speeding down the highway. Their wavelengths are teeny tiny, nobody cares. Electrons we care about. So this part, you need the idea that we care about wavelength for electrons, but you do not actually need that equation. That is another thing that is new and different this year. Team decided that we did not need that equation. Do we know the difference between particle and wave-like properties? I'm going to go with yes on this one. So in general, when we try to talk about particle versus wave, the other real part of this is that I'm going to rephrase this a little bit, that there's particle only properties of electrons. And that was essentially the Bohr model. So Bohr's model said particle only. Bohr's model also said that you have orbits and that your electrons are essentially on those orbits and that's where they stay. When you start to talk about wave properties, this is the part where I'm having a problem answering this because wave properties of electrons, this is then where we start to get into orbitals. And so this is where we come in with the Schrodinger equation, and this is where we're going to wind up with things like an S has a spherical shape, and P has this dumbbell shape, and D has either the cloverleaf shape, and it also has the whatever that thing is. 2 lobes and a donut. D is both of those. So when we talk about wave properties of electrons, a lot of that has to tie back into the fact that, like, we don't know exactly where the electrons are. That's the Heisenberg uncertainty principle. And that basically electrons have a playground. Electrons have a broad location in 3 dimensions where they might possibly be. And Bohr, when he thought it was only particles, they're just on little orbits and they just hang out around the atom. And this particle only is wrong. But that's what Bohr thought. So whereas adding the wave property is what gets us to the correct image where we currently are. The other reason why I was struggling to think about that is because you can also just talk about waves. And that's where we have things like, there we go. That's not very good. Hold on. This is where I really should just grab the pictures out of the textbook. Let's really wish that was even. Anyway, we could talk about a wave. So a wave, you either talk about it going from peak to peak, or if you can do this properly, like I usually don't, you could also talk about it being from the halfway point here to the halfway point here. Wait, no, a single wave. Did that wrong. There we go. There we go. One wave. This is the part where if you have that little bit of trigonometry, this is usually a little bit easier. So we will just go with, I guess, the peak to peak. Except I made everything as a sphere. That wasn't helpful. Where are the pictures out of the textbook? Pictures out of the textbook. For waves. Oh, don't erase everything. There we go. Those of you who don't know, I had COVID 2 weeks ago, 3 weeks ago, however many weeks ago it was. And so I had to teach class from home. Technically, my colleagues probably would have subbed in for me, but I taught class from home. Anyway, this stuff. This slide has properties of waves. So it has things like what a wavelength is and what an amplitude is, and that a frequency is a number of cycles per second. These are properties of waves. So just to clarify, I assume that original question was asking about atoms, but in the case that you also want properties of waves, there's this slide to talk about wavelength and frequency and amplitude and what those all mean. So there are also just some definitions that go with waves. But typically when we're talking about that, we're usually talking about how that relates to electrons specifically. Electrons In Bohr's model, particles only. Schrodinger's model, particles and waves, going from orbits to orbitals. Scrolling back up to my list of questions. Do we memorize the exceptions to the valence electrons? I assume that was when I was talking about these pink ones in the earlier thing. So as I mentioned, the fact that there were 5 exceptions that had to do with 5 exceptions to the electron configuration. So these are in the notes. Yes, you have to know these 5 exceptions to electron configuration. Technically, yes, that also makes them exceptions to valence electrons because these 5 will only have 1 valence electron, whereas the rest of the D block will have 2 valence electrons. I should also tell you that when it comes to valence electrons, we like to ask about some of these other things over here in the rest of this. So do know the electron configurations for these exceptions, because we do like to ask about the exceptions in terms of electron configuration. We love that. Valence electrons of the D block, we usually like to leave for the next exam. We'll ask, don't get me wrong, but we usually talk about D block and valence electrons a little bit more in the next exam, just because D block and valence electrons makes a much better story when we start to talk about ions, and ions are going to be on exam 2. So always a valid question to ask, hey, do we need to know this? I'm going to go ahead and say yes, because you should know why these 5 elements are highlighted on the periodic table. So I'm just going to go ahead and say yes, you need to know why chromium, molybdenum, copper, silver, and gold are exceptions and what they're exceptions for. Just going to go ahead and say yes. What else is on here? Do we know the equations for the de Broglie wavelength and the uncertainty principle? Not the equations, but the concepts. And that's where the de Broglie concept, this is this one. This is the de Broglie concept. Mass goes down, mass goes up, wavelength goes down. I'm not tired. So de Broglie, and as far as the uncertainty principle, uncertainty really is going to tie back into that idea of electrons as waves. So uncertainty principle basically says that the more you can know about the momentum, or we can say speed. If you're a physics person, then you just cringed a bit, and I'm sorry about that. So with the uncertainty principle, you can say things like the more we know about the speed of an electron, the less we know about its position and where it is located. And really that has to do with the fact that electrons are really strange things and they do not behave the way you expect them to. When you really start to think about electrons, quantum mechanics has weird rules in it. My favorite one of which is if something has enough energy to go through a barrier, then it bounces back and does not go through the barrier. If something does not have enough energy to go through the barrier, then it goes through the barrier. And yes, for those of you who think that I sounded like an idiot because I just said everything backwards, I did not actually say everything backwards. Quantum mechanics is in fact just that strange. That's also the reason why, honestly, why Bohr's model was wrong, is Bohr was using all what we refer to as classical mechanics. So classical mechanics are the set of physics that behave like you think they should. Classical mechanics is the one where if you drop the ball, you can talk about friction and gravity and how much kinetic energy it has and potential energy it has. You can figure everything out. Quantum mechanics doesn't do that. Quantum mechanics is a separate field of physics for a reason. So if you think it's confusing, honestly, it's a good sign because it means you've thought about it. Because yeah, electrons are weird. They really are. Okay, that's the list that the Living Learning community gave me. So that's the list I have. If y'all do have more questions, oh wait, did I have other questions? Sorry, suddenly remembered that I made a list before the review started, and did I answer even my own? Was a conceptual Bohr question look like? I'm going to say I answered that when we talked about particle and wave properties. Oh, I did want to talk about how do I choose a value of m sub L. One more quantum number thing, and then I will stop the video. Quantum numbers. So the question there, okay. So earlier in this video, we were talking about quantum numbers and how many orbitals are available in the d subshell, and this had an actual number. If I had asked a different question, but this is what we're going to talk about, is this idea of m sub L, values of L, things like that. If I had asked something like, what is an allowed value of m sub L if L is equal to 2? So I'm going to use the same general set we were just talking about. So L is equal to 2. M sub L values therefore have the same set we talked about earlier in this video, negative L to 0 to positive L. So the question that was asked was, if this is asking you for a single value, how do we pick? So if this is a multiple choice question, A, B, C, D, and E, then your multiple choice question options would look something like this. -1, 3, positive 1/2, negative 1/2, 27. And out of all of the possible multiple choice answers, only one of these actually fits the prompt. So if this is a multiple choice question, then we will set it up such that there is one correct answer. Because on a multiple choice question, we want you to select one single answer. So therefore, there has to be one single answer. If this instead was not a multiple choice question, and if this was a short answer question or was part of a short answer question, then what would happen is you would just give us any one of these. If it was short answer, then any of these 5, -2, -1, 0, +1, +2, are correct. And the key would say any of these values are acceptable. So it's always valid, because especially when it comes to quantum numbers, that often takes a couple of rounds of going through to understand it well. So always a valid question. But yeah, so any of those would be correct if that's a short answer question. If it's a multiple choice question, then we're going to give you answer choices such that you can, in fact, select one. Okay, that, I know my class probably gave me more questions. You can't see me, but I'm staring at my bag of all of the questions that I did not get to look at all of them, but hopefully this helps you guys out. Do continue to ask questions in class as we go along. We'll do our best to answer things. And at the end of the day, do your best. It's the first exam of the semester, so prepare as best you can and just be prepared to learn from mistakes, because early on in freshman semester, mistakes will happen. It's okay. The whole point of college is to learn. So we can do this. Good luck.